All right, we're going to investigate relative velocity in lesson 9. And, relative velocity and relative motion, even though we will investigate it in great detail in our grade 12 course, it's a really nice application of motion in 2 dimensions and motion in 1 dimension using vectors. Okay, so it flows really nicely from kind of what we've been doing in the last 2 lessons. And this is a really, really good application. So we're going to use vector addition and subtraction. And we're going to start in 1 dimension. Okay, so we're going to look at basically relative velocity in 1 dimension and see how we add those vectors and go from there. So let's consider several different experiments, if you will. In the first experiment, we've got a police officer who's standing at the side of the road. And he's the observer in this situation. And a car goes by at 50 kilometers an hour. The police officer uses his radar device. And of course, what speed does he measure? Well, since he's standing still, he measures 50 kilometers an hour, which is the speed of the car, or the velocity of the car. And we could also affix a direction to that. We could say 50 kilometers per hour east, as this diagram would indicate. So that's one experiment. Police officer who's an observer standing still. Let's say now, though, that we change the situation a little bit. And now we have a police officer who's driving at 20 kilometers per hour and a car going 50 kilometers per hour passes him. The police officer, thinking that, okay, this car that's just passed me might be speeding, I'm going to find out what his speed is. And so he takes out his radar gun and he clocks his speed. Relative to the police officer, how fast is the other car going? And this is probably very true when from your own observations, when you've been driving either on your own or with other people in the car, and you notice different cars either passing you or you're passing them. And if you look at the relative velocity at which you pass other cars, it's very different than, say, maybe what the velocity of that car might look like if you were standing still. And so in this case, of course, what speed does the police officer measure if he's traveling at 20 kilometers per hour and he's overtaken by a car that's traveling at 50 kilometers per hour? Of course, he'd measure, oh, that car's only going 30 kilometers per hour, because 50 minus 20 is 30. What about another situation? We'll take an aerial view of this situation, where now you've got a police officer who's driving in 1 direction, say west, and you have another car who's traveling in the exact opposite direction, say east. Police officer again is traveling at 20 kilometers per hour, and the other car is traveling at 50. What speed does the police officer measure now? What's the relative speed of the car with respect to the police officer? And of course, the police officer would measure 70 kilometers per hour. And these are all examples of this relative motion in 1 dimension, right? And why things appear to be different based on a frame of reference, based on where we're measuring the experiment, where basically how we look at an experiment changes depending on what the conditions are where we're observing it. And so basically in each of the above cases, we measured a different velocity depending on the situation. And so what we have to know is that velocity is always measured relative to a reference frame. So it's relative to what we're doing. And most of the time in everyday life, we use the ground as a standard reference frame. So if you've ever been to the airport, and I'm sure that many people have been in an airport, and you've seen those basically moving sidewalks. Those are one of the greatest tools in which to investigate relative motion, because you can really observe that, hey, you know, I can walk with the moving sidewalk, and relative to the ground, I'm zipping along. I'm going really, really fast. I can move against the moving sidewalk, so I can walk in the exact opposite direction, and it's actually like I'm staying still, if you can match the exact velocity. And so these are some of the different ways that you can observe your reference frame. If you're in a reference frame that's moving, then of course things look different. So in order to distinguish between the different velocities that are involved in what we're doing, we often use subscripts. So VOG, for example, is kind of the standard velocity of an object with respect to the ground. Right? So if you're standing on a moving sidewalk, this would be the velocity of u with respect to the ground. Basically how fast you're moving with respect to someone who's just sitting there. VMG is the velocity of the medium, which, as you'll see, is often water or air or a moving sidewalk with respect to the ground. So it's something that the object is moving through or moving on or moving with, and it's how fast that's moving with respect to the ground. So in our example on a moving sidewalk, the velocity of the medium with respect to the ground would be the velocity of the moving sidewalk with respect to the ground. And lastly, VOM is the velocity of the object with respect to the medium. And to get a really good grasp of how these things come together, we should probably take a look at an example. But the facts are is that these are vectors. And these vectors add using vector addition, just as you would imagine, that the velocity of the object with respect to the ground is equal to the velocity of the object with respect to the medium plus the velocity of the medium with respect to the ground. And you can use whatever subscripts you want. If you're talking about a plane and air, you can use the velocity of the plane with respect to the ground, the velocity of the plane with respect to the air. You can use whatever subscripts you want. These are the ones that I'm going to use to keep things consistent. So here's an example. A student swims in a river. When the current flows, its velocity is 1 meter per second east. The student can swim at 2 meters per second in still water. So if this student went to a pool, no current, nothing, this student could swim at 2 meters per second in water. Okay? So now we go to the river. If there's a current, it's 1 meter per second east. The student can swim at 2 meters per second in still water. So let's find the swimmer's velocity with respect to the ground in different situations. So let's say there's no current flowing. First of all, let's take a look at a couple diagrams. Here's a student. They're swimming. They can swim at 2 meters per second. The current's either going to help them or it's going to hurt them. Okay? And let's just state, for clarity, in this case, the water that the student is swimming in, where there's a current, that's the medium. The swimmer, or the student, is the object. Okay, so that's kind of what we have. The ground is the ground. And so we know from the problem, this is what the problem tells us. If there's a current, the speed of the water with respect to the ground. If there's a current, VMG is 1 meter per second east. We also know that the student can swim in water at 2 meters per second. Now, he doesn't have to swim in a certain direction. And in fact, those are the different cases that we're going to look at. So there's no direction there. That's his speed. So let's look at case A. There's no current. So the water's not moving. So no current means that the velocity of the medium with respect to the ground is 0. And so if we look at our equation that governs relative motion, one of these terms goes to 0. And the problem becomes very, very straightforward. Is that the velocity of the object with respect to the ground is just 2 meters per second. And it doesn't really matter if there's no current, then really everything just simplifies and it's like the student swimming in a pool. But what happens if there is a current? Here we have, again, the same thing. And if the current is flowing and the swimmer swims with the current, think about this, because you've probably had this experience where you're in a lake or you're in a canoe or perhaps you've been in a boat. If you attempt to paddle or swim with the current, can you go faster or do you go slower? And of course the answer is, well, you go faster because you're swimming with the current. So if you can swim and then you swim with the current kind of helps you along. So you go faster with respect to the ground. You of course can't go faster with respect to the water because you can only swim so fast. But with respect to the ground, you go much faster. And so here we have a situation where the swimmer is swimming east, same direction as the current. And we end up with, of course, 3 meters per second east. The arithmetic in this, the mathematics, is actually very simple. The physics is much more difficult. It's interpreting what the question means. Because in question C, the current is flowing and the swimmer swims against the current. So we know that the current is 1 meter per second east. If the swimmer is against the current, what direction is the swimmer pointed? And you should be saying, oh, if the swimmer is against the current, the swimmer's vector points to the west. And of course that's exactly what we have in C, is that we have 2 meters per second west, and then the current points 1 meter per second east. So the swimmer, now swimming against the current, can only swim at 1 meter per second in the west direction. And that's because the current's working against the swimmer. In 2 dimensions, things get not more confusing, but a little bit more demanding when we start thinking about where we put vectors and what vectors mean. What you'll see is that the method's very similar to adding displacements, vector displacements, as we've been doing in the previous 2 lessons. Right? The difficult part here is determining what goes with what and where things fall, because the wording can be very tricky. So we're going to start out with a very, very straightforward question. And then we're going to go to a question that's a little bit more in depth. So here, the same student, the same student can swim at 2 meters per second with respect to still water. And in the river, there's a current of 1 meter per second east. So let's find the student's speed with respect to the ground. If now, instead of swimming either with or against the current, the student swims straight across the river. So straight across the current. So here's our river. Let's take a look at what we have. There's the river right there. And it's we can see that the current is flowing to the east. So somebody on the ground is watching what's happening, and this person, this student that's swimming across the river, is seen to go straight across. So in this diagram, it would kind of be, from the south shore straight across to the north shore. And if that happens, we need to kind of figure out what's going to happen. If, let's say, the swimmer aims straight across. So, the swimmer's standing on the southern shore and looks to the north shore and then just swims straight across. Where does that swimmer end up because of the current? Well, he ends up downstream because the current kind of pushes him. So in this case, the swimmer actually needs to aim himself upstream if he wants to swim straight across. And we know that if we want to go straight across the river, I want to get to a point straight across to the other side, I actually have to aim myself upstream so that the current will push me back. And this is the idea of relative velocity. So in this case, here's where the swimmer, swimming at 2 meters per second, has to point himself. So that what happens is that when we add these two vectors up, we get one that goes straight across. And that would be the velocity of the object with respect to the ground. Okay. Now, what we actually have is a right angle triangle. And so the math, again, is not too hard. We're just going to use the Pythagorean theorem here, because once we sub in numbers, we can solve this in a pretty straightforward fashion. But I think you'd agree that setting it up is what takes a little bit of patience and is certainly what's going to take practice. So here, the math basically breaks down to the velocity of the object with respect to the ground is 1.73 meters per second. Now, even though we're not going to do it in this question, because we're going to look at it in the next question, we could also find the angle that the swimmer needs to travel so that he'll end up right across from the stream. And of course, that would just be one more step, and it would involve using the trig ratios and just say, oh yeah, what angle does he have to swim at with respect to north, or with respect to east, or where does the swimmer have to swim? So here's example 3. Very often, when we're dealing with relative velocities, you will encounter questions with airplanes and pilots and stuff like that. And so what this question says is that a pilot's with a heading, so that's the direction that the pilot's heading, is north 30 degrees east, and has an airspeed of 400 kilometers per hour. So this is how fast the plane can travel, 400 kilometers per hour. However, the plane encounters a wind that comes from the north. And the wind coming from the north is, of course, pointed south, and that's 110 kilometers per hour. So what's the plane's velocity with respect to the ground? So what does the plane actually do? So here it's flying 400 kilometers per hour, north 30 degrees east, but that wind is pushing it. So what's it actually doing to an observer on the ground? Well, let's take a look at what we have. One of the easiest things to point out is that we know that the wind is the medium. That's what our object is moving through. And the wind is coming from the north, so it's 110 kilometers per hour in the southerly direction, so in the south direction. Okay. The question asks us straight out, what's the plane's velocity with respect to the ground? So we know that we're finding VOG. And what that means is the last little pieces of information here are the object with respect to the medium. So we know that the airspeed of the plane is 400 kilometers per hour, and we know the direction that it's pointed in, north 30 degrees east. So let's try and put this together in a diagram. And what we find is that we have 400 kilometers per hour in this direction. The wind is blowing to the south. We add those vectors tip to tail, and our resultant is the velocity of the object with respect to the ground. And when we look at these two vectors, we say, hey, wait a second. I can add up vectors. I have no problem adding vectors. This is just a standard vector addition question. And so let's put our horizontal and our vertical chart together here. And let's look at each of these two vectors in turn. So the velocity of the medium with respect to the ground, so the wind. Is there a horizontal component to the wind? No, there's not, so it's 0. The vertical component is to the south, which in our sign conventions is negative, so we have negative 110 kilometers per hour. Velocity of the object with respect to the medium. Well, let's draw our little diagram first. Here's the 400 kilometers per hour. Here's our 30 degrees. The horizontal component of this represents the opposite side in this case. So we have 400 sine 30, which when we punch that into our calculator gives us 200 kilometers per hour. The adjacent side, which is represented by cos theta, 400 cos 30. and we get 346.4 kilometers per hour. Okay, and of course, if we go to the vector definition of kind of relative motion and relative velocity, we know that the velocity of the object with respect to the ground, so that vector is equal to the sum of these two vectors. So we just add up the individual components. So here 0 plus 200 is just 200 kilometers per hour. Negative 110 plus 346.4 is 236.4. And we have our overall horizontal and vertical components of VOG. So let's use Pythagorean theorem to find out what the magnitude of that vector is. It's 309.6 kilometers per hour. And we'll use the tan ratio to find out that the angle is 50 degrees. And we'll put these two things together and we can say very, very plainly that the velocity of the object with respect to the ground is 310 kilometers per hour. East, 50 degrees north.